Hi everyone, my name is Chris Lai, and I'm one of the programmers working on the autonomous label robot. My specialty is in software, sensors, and closed-loop feedback design. In this video, we will talk about how we can direct the robotic arm to pick up the label using a webcam as our only sensor. If you've ever worked with robotics before, you may have seen different types of sensors being used. There are distance sensors, temperature sensors, motion sensors, you name it. Sensors give a robot the information it needs to complete its task. For example, if you wanted to tell a robot to stop moving right before it hits a wall, you would use a distance sensor to provide the robot with information as to how far away from the wall it is. Then, you would write a script that prevents the robot from crashing it into the wall. Sounds easy enough, right? So in our project, we use the same principle as using sensors in robotics. However, our sensor is a camera. Now, what's special about a camera, you say? When you use a camera, either on your phone or a computer, what you see on the screen is actually what the computer sees, as the term computer vision defines. When you move your camera around, or if I move around on this image here, the image on the screen changes with the movement. Usually we call this video. What you see on the screen is actually a bunch of still images playing one after another really, really quickly. This is the same principles animators use, drawing one frame at a time to make a moving image. But why is this so important, you may ask? Well, you see, editing these still frames one after another is how we're going to identify objects. This is how we're going to be able to locate an object from the frame, isolate it, change the color of it, and even track it around the screen. In fact, you may have already come across computer vision in your life. If you've ever scanned a QR code, then you've used computer vision. If you've ever used any of the Snapchat or Instagram live filters to change your appearance, that's used for computer vision. If you've ever played any video games with augmented reality support, such as Pokemon Go, you've used computer vision. Nowadays, computer vision is all around us, which is why it's such a powerful tool to use as a sensor. So let's go ahead and run this script on here on the screen. This script is camtest.py, and its only purpose is to open up a data feed from my webcam. So when I press the play button on the top right corner, what I'll be able to see is the data feed from my webcam, which is staring down at a piece of paper. And this paper is going to simulate our label, and we are going to try to mask this out of the frame and find the center of it. Next, we're going to apply a grayscale to our frame from the last image. Grayscale will help us eliminate all the colors, so when we're trying to isolate the image, we'll only see the black and whites, and that will allow for the algorithm to easily identify the objects in the frame. Applying the grayscale filter here, I'll just copy this down, save. Now the grayscale filter edits the main frame variable and applies a grayscale to it. So I will need to change the grayscale variable down here as well before running the code. And as you can see, our frame is now grayscaled. Next, we are going to apply a Gaussian blur onto our frame here. So as you can see here, this looks like something I would see without my glasses on. It's a little bit blurry, but in fact, it does help the algorithm identify these contours easier. Next, we will apply the adaptive threshold algorithm. Now, this is where the real fun begins, because the adaptive threshold will take our blurred image and go ahead and isolate all the obvious contours. It'll display it in white lines, and it'll display everything else in black. And you'll be able to see that the edges have been highlighted by this white line. And we can obviously see that the paper in the middle is a rectangle and has been isolated from the rest. However, we can see some lines up here indicating that we may have a little issue with determining the contours because our background is not completely white. Now, as you can see here, our code base is slowly growing. The next part of the code is to find the contours and filter them out. Now, all we're doing here is we're taking the adaptive threshold data, we're finding out where all the edges are, we're isolating them from the image, and then we're just drawing a green line above them. So I'm going to go ahead and play this so you can see the effects. And you'll be able to see that we now have green lines surrounding our box and green lines surrounding the contours of the desk map. So you can see how detailed this becomes. So what you just saw there was a contour detection using the adaptive threshold algorithm. Adaptive threshold is a nice algorithm to detect many objects, but for our use, it detects way too many objects in our frame. As you could see in the previous image, it detected our piece of paper just fine, but it also detected all the contours on our desk map. So that's not good. What else can we do? Well, we can improve on this using something called Hsb filtering. Hsv stands for hue, saturation, and value. Let's pull up the color-detect.py script under our test folder so we can test out what Hsv filtering looks like with some track bars. There we go. So, the way Hsv filtering works, at least for this case, there will be 3 boxes on the bottom. The left box will show you the mask of the object. So if you change the bottom here, you will see that we gradually mask out a few colors. The center one shows your original image, and the right one shows the Hsv but with color. So the one on the left is grayscaled, the center one is the same, and the right one is what it actually looks like on the real frame, with all the colors and everything. So now we want to find the Hsv value that will isolate only the figure on the page. So we only want the white label. So we want to find out what Hsv value would satisfy that. So I'm going to increase my low until it goes black. I'm going to back away a little bit so I can see the white again. And when I see all the white, that's when I know this is fine. I can stop here. All right. So for my saturation value, if I increase this, you can immediately see my white rectangle go away. So that's no good. Now if I increase my value, you can see the surroundings on the left start to disappear. That's when I know that this is probably the right step to take, because I want to isolate the white rectangle in the center. So if I go too much, you can see everything starts to disappear. So I'm going to go, no, stay back. Value seems to be our threshold with the best results. We can still see a little bit of white stuff onto the right here, so I'm going to go ahead and decrease that on my highest value. You can see the particles are a little bit decreasing, but so is the paper, so I don't want it to go too much. And then we'll decrease the upper too, just so we get. Yeah, see, the particles on the right are decreasing now. So we are left with a blank white sheet of paper in the center with all the red colors filtered out. So our low Hsv values are 82, 0, and 126, and our high Hsv values are 179, 142, and 218. All right, now we're going to move into a very important topic. How do we manage error? How do we manage stuff if things go wrong? If we use the camera as a sensor, and we find the center of the label and try to get this information to the robot, we will 100% run into errors when trying to align the robot's 3D space with the camera's 3D space, because they're using different coordinate systems. Many times the camera will not be pointing directly downwards, which creates a slant in the image. For example, take a look at this piece of paper from vertically down and from an angle. You can see that the edges of the paper are skewing, which makes measurements inaccurate. Fortunately, there is a fix for this. It may be a complicated math term, but we will use homography to fix the angular offset of the camera. What a mouthful. All of this states is that the angle of the camera causes it to not be parallel with a flat surface, which causes measurement errors. But watch this. So this is a piece of homography script that I've written that will go ahead and correct for your angular offset error. If I go ahead and run this, we'll see that on the left-hand side here, we have a piece of paper that looks very skewed, right? The camera is obviously not looking at it from a top-down angle, because if I were to tell you this paper was rectangular, if you didn't look at the unskewed version, you would tell me I was lying. This paper doesn't look rectangular. The sides aren't parallel with the top, and the sides aren't parallel with the left and right side as well. Now, if we try to measure this with a ruler, and I can go ahead and put a ruler down right now, it'll be really hard to, because the measurements on the ruler don't match with the measurements on the screen. When we deal with the robotic arm, it's getting measurements from data that's on the screen itself, and we need to map that to the data in real life, which is why it's really important that we get equivalent values. Therefore, this is the need for our homography algorithm. When we unskew the image, if we look at it side by side, we can see that the right image looks more nicer. All the 4 corners are mapped to each other and form a rectangle on the top left corner of the screen. And if I move my paper here it'll attempt to find the correct location for the paper. And the way we like to do this is that our ABCD points are mapped to the top left corner of the screen, which allows for the maximum angle possible. So we don't get black spots from our homography algorithm cutting out the screen. Alright, so I want to get the script to a point where I can move my piece of paper, and I don't want the stuff on the right hand side to move. I don't want it to go all crazy and stuff. I want to lock it in place. And it's pretty simple. All I need to do is I'm going to comment out these 3 lines. These 3 lines calculate the new matrix such that it will try to calibrate it in place. However, if I don't do anything, if I just comment these out and run the script again, look what happens. You see here on the left side, which is the real one, and on the right side, which is the corrected version, if I move the piece of paper, we can start to see that the run on the right side won't change. The one on the left side is the skewed version, which does not have the homography, and the right side does have the homography. Just look at the difference. It's insane. The one on the left has slanted edges that are not parallel to the top, bottom, left, and right edges of the screen, and the right one is. It's much better. So now, if I go ahead and try to measure things on the right here, you can even try to put objects inside the frame, as they would look really cool. So I could put a pencil here. You can see that the pencil on the left is real and slanted, but it's corrected on the right side of the image. So we can go ahead and measure the screen now, and it'll map itself to the measurements in real life. And by sending this data over to our robotic arm, this will cause the robotic arm to be much more accurate than if we hadn't performed this task. This eliminates the need for precise setup. We can just set up the camera, and the rest can be done in post-processing through software. That's all for the Sensors and Computer Vision team for the ROBOTIS Autonomous Label Robot project. I hope you learned a thing or two as to how our device works, and I wish you the best of luck for your own experimentation. Thank you for watching, and have a great day.